I approach this afternoon, speaking in your Pioneer series, with very mixed feelings. On the one hand, it seems to me that it's not very long ago, and somehow or other we must all have been there together, and therefore you know as much about the early days as I do. On the other hand, in the intervening years, I have occasionally gotten a glimpse that suggests there may be a generation gap. I am reminded of 3 or 4 years ago when I was giving a lecture to a group of chief economists of major American corporations after dinner at a meeting in Washington. And during dinner, at tables of 8 or so, my host and I were seated, and on the other side of this table were 2 or 3 empty seats. A man came in and sat down and was introduced to me as a man who was the chief economist of IBM, now retired. And he paused a moment, and you could see the mental computer clicking and the correlations working, and suddenly he brightened up with the result, and he said, "Was it your father that invented the magnetic core memory?" Another glimpse of what has happened has come to me as I attended technical meetings. I began in computers as a research assistant, and the first technical meeting that I went to was one of a worldwide convocation of all 20 or so people who were interested in computers. Now, to understand that meeting, you have to understand the definition of the times as to what a computer meant. A computer consisted of a girl sitting at a desk with a mechanical desk calculating machine. Another measure of how long ago that was, it was socially acceptable to speak of a girl at the desk, even though she was a young woman. It was also socially acceptable to type jobs by sex. So you see, we have indeed changed a great deal. But I progressed from that meeting to giving technical papers in technical sessions, and then to being chairman of technical sessions, and then at one stage giving the after lunch or keynote address. And then after I'd stopped working in computers, I would go back to meet my friends and those of us that had worked in the computer field. And then finally, I went to a meeting once of 30,000 computer people. I didn't meet a single person I knew. There wasn't anyone there who had ever heard of me. And I decided I shouldn't ever go again. The story of Whirlwind has many angles and facets. It's a story of new concepts, new components, and new applications. It's also a story of a continual change of direction, building always on the past and what had been accomplished to that time, but raising and changing the objectives as new possibilities unfolded. For a quick preview of the history of the Whirlwind project, it started as something very different from what you have seen in the movie and in the comments so far. It started as an analog computer for determining the stability and the control characteristics of large aircraft. It was to be a far more advanced version of the kind of trainers used even today for training pilots in aircraft. It wasn't to train them for a known aircraft, but to take the equations of motion and the physical dimensions of an airplane and anticipate what its behavior would be, since at that time many airplanes were being built that did not control properly and did not behave well after they were finished. The idea was to simulate an aircraft with an analog computer. We took about a year to decide that any analog computer big enough to do that job would end up presenting you with a solution of its own idiosyncrasies rather than a solution of the problem at hand. And so there was a shift to serial digital computers, which were then very much the vogue, and a year was spent deciding that a serial digit transmission computer would be too slow. That was the year of 1946. 1945 had been spent in dismissing the idea of an analog computer. 1946 was spent in dismissing the idea of a serial digital computer. 1947 was the beginning of what became Whirlwind, a parallel, high-speed, synchronous machine that very soon dropped the original purpose of being an aircraft simulator and shifted over to being directed toward real-time control, in particular combat information centers, initially for the Navy, to analyze and coordinate the information from a group of radars on different ships, from submarines below the surface, and from airplanes above the surface. 1950 or 51 represented the beginning of operation of Whirlwind, and it also represented another transition away from the interests of the Navy and toward the use of the Whirlwind computer to demonstrate the feasibility of a computer-controlled air defense system. In 1951, there was a project assembled at MIT, which came about, I think, because a proposal had been made to use high-speed digital computers for the North American Continental Air Defense System at a time when the Air Force knew that its manual system was inadequate, and when there was no alternative. And then here came what appeared to be a completely crackpot and harebrained idea of using digital computers, proposed at a time when no high-speed electronic digital computer had yet operated, and proposing to use these across the whole North American continent. The Air Force was in a tremendous bind. They did not dare say no because they had no alternative. They did not dare say yes to anything this radical. And so the solution engaged in under such circumstances at that time was to convene a prestigious review group to look at the whole situation. Harry Nyquist of control fame at Bell Labs was a member. Groves, the general who was associated with the Manhattan Project on atomic energy, was a member. The chief of staff of the Canadian Air Force and the British Air Force were members. MIT, to remove itself from being too directly involved in the outcome, brought in Wheeler Loomis, head of the physics department at the University of Illinois, to head the project. During the time that that project was in session, Whirlwind actually demonstrated intercepts that I will come to later. This led to the establishment of the Lincoln Laboratory and eventually to the SAGE air defense system. To appreciate the story and to appreciate the film that you have just seen, one has to make the strenuous effort of putting oneself back into the circumstances of 1946 and 47 relative to digital computers. There was no mention of electronic digital computers in any of the MIT courses. Analog computers were being developed. The mechanical differential analyzer, the Bush differential analyzer, had been finished prior to my coming to MIT in 1939, and various more advanced analog computers had been developed. But I think the conditions of the time are revealed fairly well in a quotation I would like to read, which I have picked up from a history of Whirlwind, which is a part of the history of the MIT Electrical Engineering Department, written or in the process of being written by Professor Carl Wiles. And this is a quotation from the master's thesis of Perry Crawford, written in 1942. And in the thesis he says, during the last 5 years, Bush, Caldwell, Overbeck, and others in unpublished memoranda at MIT have described methods for performing arithmetical operations with electronic devices. Recently, it has been proposed that electronic calculating systems can perform a valuable function in fire control operations. It is the purpose of this thesis to describe the elements and operation of a calculating system for performing one of the operations in the control of anti-aircraft gunfire, which is, namely, the prediction of the future position of the target. It is to be emphasized at the outset that little progress has been made toward the construction of automatic calculating systems for any purpose. Effort to the present time has been confined to the development or even invention of fundamental elements of electronic calculating systems. The system described in this thesis must therefore be regarded as tentative and in a large measure arbitrary, because it is not based on experimental evidence. It can be proposed only that this thesis shows a possible approach to the design of a number of calculating system elements and to the structure of an arithmetical predictor. There was, however, a certain amount of preliminary work going on in computation and in electronics applied to computation, although the main thrust of electronics during World War II was toward the development of radar. And it is from radar in the post-war world that some knowledge of video circuits remained, that two devices that had been developed in radar for detecting moving targets required the memory of one sweep of radar echoes so that the next sweep could be compared with it, the requirement of remembering a long waveform from 1 millisecond to the next. Two devices had been developed for this. One was to send the wave shape down a column of mercury as an acoustic wave, picking it up at the other end so that as it became available, it could be compared with the next incoming signal. And the other was to store the signal as a charge on the inside of an ordinary cathode ray tube in such a way that when one swept that area again, one could pick up on the outside through an aluminum foil capacitor spread over or electrode over the outside of the tube, could pick up a signal that could be amplified and used for comparing the past scan with the future. Both of these were used in the early days of computers. The cathode ray tube became better known as the Williams tube after Williams in England, who had refined it into something that was nearly workable for computers. And the mercury line was indeed reliable. It was a sound idea. The people at the University of Pennsylvania used it. Its disadvantage was that it rather committed the architecture of the machine to be of serial digit transmission, therefore slow. Any set of pulses stored in that mercury column were available only after a millisecond or more, so that you had slow access to them. At about the same time, when we first began to make the transition from analog to digital computers, incidentally, I might say a word about that transition, because Perry Crawford, whom I have already mentioned, has had a very important part in the whole history of the Whirlwind development. It was he, as we stood on the front steps of the main MIT building one afternoon, as we discussed the problems of analog computers for this aircraft analyzer, Perry Crawford then being a technical officer in the Special Devices Center of the Navy that were the contracting officers for that project. As we discussed the difficulties, he suggested to me that I ought to become aware of what was going on in electronic computation. I believe it is the first time that the field had been called to my attention, or that I even knew that there were in fact some active projects. There were two projects in particular. There was the ENIAC project at the University of Pennsylvania. ENIAC was not a general purpose machine, but it was electronic. It had 18,000 vacuum tubes in it, and it was programmed by trays of wires that one would plug in to various places and manually plug up the sequence of computations that were to be carried out. In no sense is it a modern general purpose machine, but it was electronic, it did function, and it was used for computing ballistic tables for the Army to be used in connection with field artillery. The other major project that was already well along, near completion at the time that we first turned our attention toward digital computation, was the Mark I computer under the leadership of Professor Howard Aiken at Harvard. The Mark I machine is probably best described as finally a working embodiment of the ideas and designs that Charles Babbage had first proposed around 1850. There is a very good treatment in various books and manuscripts of the Babbage work. It was indeed very insightful, laid out the possibility of calculating machines under their own internal control. The Harvard machine was a 23 decimal digit machine, decimal digits, 23 decimal digits. It stored 72 such numbers. It was controlled by a punched paper tape. It had a third of a second add time, a 6-second multiplication time, and a 16-second division time. It is the first and last machine to have a truly major psychological impact on the observer. You could hear it, you could see it, and everything progressed at a speed compatible with the human senses. Since then, computers have become nothing but boxes that you have to assume something is going on inside of. Let me turn to some slides, a number of which you've already seen in the movie, but we will run through them anyway. Are you able to see those back there? This is the control center and the point one would first make his acquaintanceship with the Whirlwind computer. There is a scope in the center of the panel, which through a probe system could be connected to any part of the machine. There were register lights that allowed one, if the machine were stopped, to see what was in any registers. And over to that slide is backward. To the left, but what you see on the right is the main room of the computer. That main room looks like this. It was indeed a walk-in machine. It was a machine of some 4 or 5 rows of equipment extending down in each side. I was going to say 8 feet high, but I suspect that Ken is right. It probably was 11. I didn't have the figures actually at hand. You see over on the left in the second row, 2 vertical boxes, which are the storage tube boxes at a time when the Whirlwind computer used electrostatic storage tubes for its storage of orders and partial results. Now, there are problems that we faced at that time that seem always to be in front of every designer. I was reading just the other day about the difficulties of making a machine small enough to work at some of the highest speeds that are being talked about today, so that the propagation time across the 3-inch size of the machine wouldn't upset the timing. Well, that was a problem in Whirlwind. There was a problem of the physical size of the machine beginning to be comparable to some of the timing sequences that one had to keep control of. There was a 1/10 microsecond rise time on the pulses that were used. I believe that that represents about 90 feet of transit, and the machine was just about that big. So that we did have some concern, it was not a serious problem, but some concern about that perennial problem of the relationship between speed and physical size and the speed of light. The racks into which equipment were mounted ran down the aisles to the side. It was a 16-bit machine, 8 on each side of the aisle. As Ken has mentioned, a rack for each digit column, and with transfer buses across the top of the machine. All transfers were checked. They were sent to where they were to go. They were received. They were sent back to a check register to see if they had indeed been received properly. Probably an unnecessary precaution. But at that time, there was almost nothing known about what noise would do in circuits at these kinds of speeds and under these extreme demands for reliability. Here you see a glimpse of the power room. There are some motor generators in the back. It is the first time that anyone of our generation, at least, had ever seen a 1 farad capacitor. I understand they do exist these days, but a 1 farad capacitor at 200 volts stores a great deal of energy. If I did my arithmetic right, it's enough energy to lift a 1,000-pound weight 14 feet. It provided perhaps the most rapid electronic fault correction that I have ever encountered. These capacitors were made up of electrolytic capacitors, many of them plugged into sockets and connected in parallel. If one of those capacitors should age and short out, the entire 14,000 foot-pounds of energy were discharged through it. This blew the capacitor apart and out of the socket, so there was no further trouble. Here is a picture with Bob Everett and I believe Gus O'Brien of the control matrix of the machine. The entire machine was large, open. Every connection could be gotten at with a scope probe. This is a double decoder, one in which the machine orders, 32 of them, the 5 binary digits of representing one of the 32 machine orders came in, selected one of 32 lines, which crossed another matrix that was driven by an 8-position clock, so that it was possible to put out a timed sequence which would drive the machine in a synchronous controlled manner through whatever order had been inserted into the input of the control matrix. It was a 16-bit machine. 5 of those bits were used for defining control orders, and 11 bits sufficed then to define the positions of 2,048 16-bit words of high-speed storage. The problem of explaining the nature of a digital computer to students, to users, to the public, was of quite a different order of magnitude at that time than now. There was no appreciation whatever of the nature of such a machine, and one had to draw on such analogies as he could. And the analogy that was familiar to people at that time was this kind of computer. And so we would point out that the control element is the person, the arithmetic element is the mechanical adding machine, the notebook represents the storage, and that the digital computer simply did all of this very much faster and with fewer drops of perspiration flying about. That is from a booklet written in 1951 to illustrate the nature of computation, and it was appropriate and timely in those days. Here is an engineering predecessor to the Whirlwind computer, the so-called 5-digit multiplier. Norman Taylor, who was chief engineer, is beside it. This was an exercise engaged in to find out something about the reliability of the kind of circuits with which we were working. What would be the nature of noise? Nobody knew what kind of thermal noise or pulses might come along that would trigger flip-flops or gate tubes into passing a spurious pulse. And no one knew what kind of unknown effects could control or influence the reliability. This device was built to carry out a repeated multiplication every time, comparing the result with a preset answer to check every multiplication for error and to report any errors that occurred. We found that it was prone to errors in the middle of the night and traced some of these to passing streetcars. We also traced some of them to the starting and stopping of elevators in the next building, all of which led to the realization that for the kind of accuracy, also out of that, we determined that power lines then, and I suspect still, are given to having missing cycles on them as the automatic switching in the power system comes and goes. The result was something like 150 horsepower motor and synchronous generator to isolate the entire Whirlwind system from the line through the mechanical inertia of the synchronous machines. A process that may still be used, although a greater likelihood that one can these days carry through that kind of difficulty with capacitor filtering. The control center again, Jack Gilmore, I believe, standing at the controls on the left. And out of sight to the right, a cathode ray tube that you saw in the movie a while ago. In front of Jack, to the left and about waist high, is a telephone dial, if you can see it. And this was part of the marginal checking system that's been alluded to. The marginal checking system was a very important part of Whirlwind reliability and of the succeeding Sage air defense system. I remember very clearly the genesis of the marginal checking system. Whirlwind underwent approximately an annual investigation by the sponsors, sending in various outside advisors to find out how it could possibly cost so much and take so long and be apparently so useless, because these sponsors were, for the most part, interested in scientific computation. They did not see that a 16-bit register length was of any use, and in fact there was a very substantial communication gap most of the time between the project and the Office of Naval Research that eventually became the sponsors after it was transferred from the Special Devices Center. That story is told very well in the history. I won't go into much of that contractual, political, and financial aspect of the project. But the marginal checking system, which added a good factor of 10 to the reliability of Whirlwind and the succeeding systems, came out of the rather unlikely circumstance of an investigation of the project by a mathematician. Francis Murray, I believe of Columbia University, had been nominated by the Office of Naval Research to come and see what we were doing and to evaluate it. I believe it was on a Saturday because he couldn't get away during the week, and as we sat in my office at one point, he raised the matter of reliability, and we told him how reliable the vacuum tubes were and what we had done to increase their life, and he thought that was very nice, but he said, even so, sooner or later they're going to deteriorate, and as they get down toward the edge of an operating range, you're going to find that outside noise, streetcars, and anything that might happen is going to cause intermittent and very difficult errors to find. It struck me as a remarkably penetrating comment that we really hadn't given enough thought to. And it seemed to me that he was taking it very seriously and something had to be done. So I stalled him a moment and we talked about one or two other things, and I tried to figure out what you would do about this kind of a problem. And I suggested to him that we might be able to lower some of the voltages on the tubes enough to find out if they had an operating margin between where they were running and where they would cause trouble. And he seemed to think that was a good idea, and we reviewed it the next Monday, and we decided it was a very good idea, and we proceeded to put it in the system. What that did was to allow us to find, before they caused their first mistake, all vacuum tubes which were gradually shifting their characteristics. Not only did it find vacuum tubes, but any circuit components associated with them would also be found. This was above and beyond the improvement in vacuum tubes, which had come about through a process of being very concerned about that 500-hour vacuum tube life that was mentioned a moment ago. 500 hours, as you go to machines of thousands of tubes, simply is not enough to have an acceptable mean-free period between failures. Our looking into the question of life revealed a number of interesting things. First of all, the failure of vacuum tubes in those days meant low emission, and all the simple testers that were used for testing radio tubes simply found out what the tube would emit in the way of electrons in a steady state circumstance as read through a meter. On the other hand, we were aware that the radar people had been getting these very high power, very high pulses, not only out of spectral tubes, but also out of ordinary tubes. Tubes that were supposed to be rated at 20 milliamperes were sometimes used to put out a pulse of 1 full ampere, indicating that there was lots of margin there somewhere under some circumstances. And we began to look at such tubes, and we began to pulse them into the positive grid region, drive them very hard to see where this high current would come from. And we found that indeed one got a very high current initially, and in 2 or 3 microseconds it would decay off to an unacceptably low value. And it had all the characteristics of a tube that has a resistor capacitor cathode coupling circuit in the cathode. And we began to ponder how that could be. And where was this resistor and capacitor that was giving it the characteristics? It turned out, with a few people with electron microscopes and advice from various ones outside of our group in the analysis of the materials, that in fact the capacitor existed in the cathode of the tubes as a very thin barrier of silicon oxide probably, on the surface of the nickel underneath the emitting oxide of the cathode. It was so thin that it would pass a 1 ampere pulse for a fraction of a microsecond, and then it would charge up, and it had such high resistance that it then would self-bias off the tube. When we dug into this more, we found that this silicon that was causing the trouble was being intentionally put in vacuum tubes because it accelerated the processing time on the tube making machine so that you could sell the tubes for 47 cents. Having found the problem, we started to get tubes made without the silicon. They were more expensive to process. They had to be on the vacuum much longer. They had to be heated more, and one thing and another. But the upshot of that was that in one design step, the life of vacuum tubes was raised from 500 hours to 500,000 hours. And then another factor of 10 on top of that with the marginal checking system that took out all of the tubes before they caused a mistake that were undergoing gradual deterioration. The one thing that was left was the mechanical loose weld, the break, the physical mechanical break in the vacuum tube that might occur suddenly was the remaining uncertainty. The marginal checking system and the programs that went with it, because one would lower the voltage on one cross-section of the machine, then run test problems to see if that part of the machine would carry out its work properly, led to machines of extremely high reliability and furthermore a great deal of diagnostic self-checking. We arrived at the point where you could send somebody out into the computer room and say, go out there someplace, anywhere you would like, and bring back a vacuum tube out of a socket. And by the time he'd gotten back, the computer would by itself have typed out the location of the socket with its missing tube. The bouncing ball experiment you've seen even more dramatically in the movie. It is a cathode ray output that was used for scientific problems when photographed. with a camera, and eventually was used in the prototype of the air defense system. The Whirlwind also developed the ability to communicate with the machine by bringing a photocell up to the cathode ray tube, indicating that part of a picture in which you were interested or you wanted to designate to the machine. And the machine, knowing where it had just put a light pulse on and receiving a feedback pulse at that moment, would know this is the part of the picture that you want to do something about. And the beginning of the real-time man-machine interaction. Throughout the development of Whirlwind from 1946 through 1953, the one technical problem that dominated more than anything else was the matter of what kind of storage to use, how well would it work, and would it be sufficient. Perhaps there's a parallel here to your design problems today. I understand the nature of the storage, what it will do, still may determine architecture and possibilities, but certainly not to the degree of intensity that it did at that time. Here you see Pat Utes and me examining the behavior of one of the storage tubes in one of the digit columns, one of the bit columns of the storage row. We started off with a cathode ray tube of our own design, a rather complicated one because we were not very much impressed by the low signals and the difficulties of the Williams tube. This was a tube that had two cathode ray guns in it, and it had a secondary emission surface on the face and a screen in front of that secondary emission face, and the ability to store either plus or minus charges on that dielectric surface in such a way that the flood gun, a gun that flooded the entire surface with electrons, sustained either a positive or a negative charge. The negative charge was sustained by collecting electrons that impinged on it, and the positive charge was sustained because it was enough more positive that the electrons hit with enough greater velocity that they knocked out more electrons than came to the surface, and those extra electrons went back to the control grid, so that the tube had two stable states, a more positive and a less positive charge within the tube. Then, of course, we found the boundaries between these began to grow and change, and one had to break this surface up into a mosaic to provide physical boundaries so that the charge boundaries couldn't move. And there was essentially one problem after another, and the storage tube operation was touch and go all the way. It finally did arrive at a point where it was working, and for a period of time it served the purpose, but rather expensively. We had tubes that would store 1,000 bits. They cost about $1,000 to make, and they lasted about a month. That's $1 per bit per month of maintenance cost on the memory, which is a fairly expensive operation. There was a desperate search for better memory. We seriously considered at one stage renting a television microwave link from Boston to Buffalo and back, so that one could store something like 3,000 bits in the 3 milliseconds of round-trip transit time. Throughout the middle years of the project, from 1949 to 1953, we were in the position of having to radiate confidence about the storage tubes being good enough, while at the same time knowing they weren't. And it was in that climate that the development of the magnetic core storage took place. Actually, that development began in 1947 in an effort that I'd made to use glow discharge tubes in a matrix arrangement for storage. But again, they depended on secondary emission, they depended on gas discharge, they depended on the life of the device, the characteristics would change, it would depend on pressure and temperature, and it took very little experimenting to discourage us from going forward with that line. Then for a period of 2 years, we struggled with storage tubes, but kept in mind the possibility, the desire for a three-dimensional mode of storage. It was out of reading, looking at an advertisement in an electrical engineering magazine, and observing the characteristics of a material called delta max that I undertook to take that nonlinear material, that rectangular hysteresis loop magnetic material, and see if it could be embodied in the general concepts of a three-dimensional memory. Delta max was an outgrowth of a material that had been developed by the Germans in World War II to be used as magnetic amplifiers. And the company then selling delta max was in fact selling it as core material in magnetic amplifiers that would be biased by direct current to control the alternating current flow through the transformer. A theoretical scheme was worked out. The diagrams of that time are almost exactly what was then used for the ensuing 20 years or so, and yet one had no way of knowing whether the theoretical structure would work or not. There was nothing known about magnetics except in the full hysteresis loop of driving them from one side to the other. No knowledge as to whether if you drove them through half of this pattern you would in fact retrace where the diagram suggested you would, or would the whole magnetic polarization collapse and disappear, and with it the storage. Nor was there any real knowledge on the part of any of the experts in magnetics as to whether or not repeated activation might change the crystal structure or the control characteristics. All of these things had to be determined as we went along. Initially, the material was metallic. It was a wound metallic tape. Expensive, difficult to work with. It was an especially heat-treated tape that was pressure sensitive, and therefore each little coil of metallic tape had to be protected from pressure by putting it inside of a plastic bobbin. And so you see these little coils of magnetic tape inside of what look like small threads for spool for threads. The metallic tape in these was as thin as 1/8 of a thousandth of an inch because the eddy currents would otherwise prevent the material from responding anywhere near quickly enough. Even so, they were slow. Another turning point came out of the technical literature. I was perusing an article by Ernest Albers Schoenberg, a German ceramicist then working for the General Ceramics Company in New Jersey. And they had been selling ferrite cores for use in television yokes and television transformers. And the difficulty with ferrites for that application was that they had an open hysteresis loop which represented energy loss as you went around the magnetic cycle. And this whole article was on the matter of how you might reduce the openness of the hysteresis loop and thereby get better behavior. What we of course wanted was the opposite. We would like to have a more open hysteresis loop with more loss, with the potential of its holding a magnetic state. Again, no idea of whether it could be done, and we sent out feelers far and wide. We knew that the ferrite development had been done primarily at Philips Eindhoven in Holland. We got word to them and asked them about the possibility of making rectangular loop material from the ferrites, and the answer was that enough was known about the theory to know you could not do it. However, that usually didn't discourage us, especially since there was evidence of openness already, even in the published literature. The initial ferrite cores were large. The first ones were even larger than this. This is a 16 by 16 array of cores made by Schoenberg. And he was indeed a remarkable man. He demonstrates that time after time, the art is far ahead of the science. He was able to make magnetic ferrites that would work in magnetic core storage out of his background of having made pottery in Germany. And I never watched him work, but one of our people who watched him work said he would put his hands in this black powder and run it through his fingers and say, "That feels square to me." And then he would press it and fire it. And every once in a while he would get a batch with a few percent of cores that in fact were usable, which at the very least demonstrated that it could be done. It took MIT 2 years, probably $500,000, and the best talent we had in electrical engineering and physics to match what Schoenberg was able to do. By that time, we understood the 50 or so variables that were involved and could make essentially every batch turn out to be 98 or 99% yield. But the real start was through art and trial and error, as it so often is. The work progressed from the initial ideas in 1949 to eventually a memory large enough and complete enough that it ought to be tested. By that time, the Whirlwind computer was being used in the early air defense experiments, and we didn't want to upset it with an unproven memory. And even though these memories worked perfectly in individual planes, we were still very much an adherent to Murphy's laws, and we suspected there were still things we didn't understand and that ought to be tested in some full-scale manner. It is my recollection, partly reinforced by Norman Taylor reminding me every once in a while that I contended that Ken Olson would not be able to make a full-scale computer in 9 months for testing this memory the way he wanted to, and I was much opposed to it, although he had the backing of Norman Taylor, the chief engineer, and perhaps it was part of the spirit of the laboratory that even though one didn't believe a proposition, sometimes you let it go ahead. In fact, it succeeded brilliantly. And in the spring of 1953, the memory test computer was running with the first bank of 32 by 32 memory. It worked without a flaw, and by August, 3 or 4 months later, that bank of memory had been moved into the Whirlwind computer, and the electrostatic storage tube operation, with a great sigh of relief, could be closed down. The magnetic memory had a number of interesting aftermaths and incidents. It provided almost a lifetime legal career for R.J. Horn, patent attorney, who started on it actually as a student when he was going to law school, and if he's finished with it yet, it was only in the last 2 or 3 years. The lawsuits maintained a fairly steady pace, the last one being filed 2 or 3 years after the expiration of the patent. Along the way, when it came time to file a patent on the magnetic core memory, the research corporation that then administered patents for MIT refused to pay the filing charges because they said there was no possible future commercial use for such an idea. Eventually, MIT paid the filing charges, and thereby led into years of litigation. As I recall, it took about 7 years to convince people in industry that the magnetic core memory would work, and it took the next 7 years to convince them they had not all thought about it first. A very, very extensive legal education went with that, and I suppose the patent defense took 1,000 times as much of my time as I ever put into the memory itself. All through the period from about 1949 on, 48 on, actually, there was an evolution of the Whirlwind computer toward the real-time military control system idea. The first reports suggesting a digital computer for managing combat data were written in 1948. They were written for the Navy. The Navy then ran out of money, and the Air Force was beginning to feel the fear of a major bomber attack on this country, and had found themselves without a satisfactory air defense system. And eventually, the Whirlwind computer became the computer operating in an experimental control center called the Cape Cod Control Center that linked together several radar sets and sent controls directly to the autopilots of interceptor aircraft. This is fairly well along. You see a group of a dozen or more military officers sitting at consoles, each with his own specialized map display covering that part of the military operation that he was supposed to pay attention to. And as you see in this figure, had a light gun, cathode a photocell that he could signal the computer what part of the display he wanted action with respect to, and various switches that he could set saying what that action was to be. In the upper left, the small tube was a Caricatron tube. I don't know whether these are still in use, common or not, but the Caricatron tube, which was developed for this project, had down in the electron gun a double deflection system, and the first deflection put the beam through a mask that had the full alphabet and the full set of numbers on it, and then refocused and redirected that onto the screen so that you could print characters that were actually from the shadow mask. I don't know what the state of that art is anymore, or whether it has survived. In connection with this system, we encountered, I suppose, the usual number of new problems. And we discovered that the radar set out on the end of Cape Cod kept sending us rather frequent erroneous signals for no reason that seemed to arise from either the radar set or the Whirlwind receiving equipment. And eventually, we decided that it was coming out of a telephone exchange down around Falmouth somewhere. So we got in touch with the Bell Laboratories and the people that know about such things in the telephone system, and we asked them what they knew about noise in switching systems and what were the specifications for the amount of noise and disturbance that could be on a telephone line. And they said, the specification for a telephone line is that you shall be able to understand speech over it. Which again marks a fair difference from today. I was putting in a new high-speed console the other day, and I find the telephone company will give you a whole set of tables with the probabilities of how many errors versus how many miles you have dialed up the telephone system. We're back again to the control room near the end of the Whirlwind's active life at MIT. You can see under the clock a panel that perhaps you can see is not electronics. That panel has in the middle of it a hand grenade that says the pin is to be pulled on January 30, 1959. The idea was, I believe, that that was the end of Whirlwind. It was not, however, blown up. It was taken apart. It was taken apart and put in a warehouse. And much to the surprise of all of us that knew anything about the machine, it actually was reassembled by Bill Wolfe in Concord and used for perhaps another decade. I would never have thought that machine could be put together again once it had been taken apart, but it was. All of the interconnections in the machine were by coaxial cable. It was a mass of coaxial cable with expensive fittings on each end going into plugs around the edges of all of the panels. Now, There was more to the project than developing equipment. There was the proposing of applications, the convincing of people that the digital computer was here to stay. And one of the more interesting exercises during that time was a forecast made in 1948 for what would be the state of computers in the military establishment for the next 15 years. It suggested that the field would arrive by the end of 15 years at the need to train 4,000 people a year. And perhaps the flavor of the report can be obtained from a final diagram, which I don't expect you to read. A diagram of about this size, in which a dozen or so military applications of computers were listed down the left-hand column, and the 15 years of the forecast across the top, and each square, in other words, the square for each application for each year was filled in terms of what would be the state of that application in that year, how much money would be spent in that year for R&D and for prototype production and for production equipment. I think these are redrawn to get legibility, but here's the lower right-hand corner of the diagram, September 14th, 1948. Now we will look down the left-hand two columns, in which we find applications for engineering and science, for basic research, for training, for data conversion, including physical to digital and radar set to digital conversion. And further down, engineering and scientific computers, fixed location control systems, including aircraft interception, air traffic control, manufacturing process control, and simulation systems for design studies and for war college training. Bear in mind, none of this had been done, and no high-speed electronic general-purpose computer had yet operated. I think that's probably a defendable statement. The Harvard machines, and Howard Aiken was an excellent engineer and turned out remarkable machines, were not particularly high speed. The ENIAC was not general purpose. Semi-mobile control, shipboard combat information centers, fire control, mobile systems, and airborne computers. After going through the Whirlwind computer room and being surrounded by it, it took a certain amount of nerve to talk about airborne computers. And logistics, management information system, in other words, and then costs. And the costs were tallied in total yearly cost, total yearly for research, total yearly experimental construction, total yearly production, and the number of staff required in each year. And down in the right-hand corner were the grand totals of these numbers. Focusing on the second one, for research, these are in millions of dollars, it suggested that in the 15 years, $1.1 billion would be spent for research in the computer field. If you follow these entries across, you will find in general the field came along faster than we predicted, but I think the time and the costs are probably at least as close as most people's estimates today for the development of the next machine that's to come out of the factory. In other words, they were not off by more than 20 or 30%. And that was accomplished by breaking that entire 15 years and every piece of it into elements that consisted of not more than 20 people working a calendar quarter. This was assembled with an identification of tasks in every category for 15 years, leaving the time necessary to evaluate results, leaving the political time necessary to get financial backing, and building up this entire sequence out of very small pieces, 3 months' work, by small groups of people, to each of which a task had been identified. Now, this report was taken by us into a meeting with the Office of Naval Research in which they thought the subject was to discuss whether or not we got the next $100,000. It led to a communication gap. Crystal balls were sometimes cloudy, and in various areas, different people's were more or less cloudy. I think ours is pretty good in the chart we just saw. Howard Aitken, for whom I had a great respect, was a wonderful engineer, made the first 3 machines that really worked well. Nevertheless, lacked a really sweeping vision of the field, and he was quoted as saying once that if all 3 or 4 of the digital computers then under development should by any chance work, it would more than saturate any conceivable future use for such machines. And this was because he was primarily interested in the computation of mathematical tables, books that you would then look up various mathematical functions in. And he finished his 20 volumes of the Bessel series functions about the time that people were shifting over to computing any particular mathematical function on the spot when you wanted it and throwing it away and never again looking these up in tables. But of course, our own crystal ball wasn't all that good all the time. It fell short in many areas about the drama of the future. Not even in our most brazen moments would we have suggested the client in whose behalf a computer was soon to be invoked. Only 20 years after Whirlwind was being designed, a digital computer selected a friend of ours to become the Episcopal Bishop of Delaware. So we certainly didn't anticipate all of the possibilities. Now, a project of this sort grows out of a background that's very important if it is to take shape and to succeed. MIT has, through the years, particularly at that time, been a kind of a free enterprise society in which anyone could do anything that was honorable if he could raise the money for it. And many of us had our initial training in the servomechanisms laboratory under Gordon Brown. He ran a remarkable place. It was traumatic. It seemed to me at times like the most poorly managed place one could ever imagine. It turned out that it developed a remarkably high percentage of people who went on to be leaders in their field. This trauma was a time of training. It was encouragement, but it was also being left to yourself, competing with other people for resources. It was a crucible into which people were thrown, and they succeeded or not, as the case may be. And those that stayed with it came out tempered in a way that allowed them to go on to many kinds of leadership positions in the future. It was also Gordon Brown who, as World War II was beginning to close, called me in one day and said, I have a list of projects here, 8 or 10 of them on the sheet. Are there any of them that would interest you to work on next? And one of them was this stability and control analyzer for aircraft, which was the beginning of the sequence that we have just been through. Then there was Admiral de Flores of the Navy, a very practical person who had developed aircraft trainers during World War II, who had a special insight into the nature of Navy politics. I know that we went to him once to see if we could perhaps get another $50,000 in our budget. And he said, it's impossible. If you'll ask for $10,000, I can approve it myself. If you'll ask for 200,000, it'll be big enough that I can go to the Secretary of the Navy for. But 50,000, there's no way. And behind all of this, a man named Nathaniel Sage, Nat Sage Sr., who was a tower of strength in times of technical and managerial difficulty. He was a civil engineer by training. He had grown up as a child in army camps around the world. I believe that his father was an army officer. He was an excellent judge of people. He was absolutely sure of himself, right or wrong, in his judgment of people. And there were those around MIT that he wouldn't trust any further than he could see them. And then there were others, like Stark Draper, Gordon Brown, and me, who seemed to enjoy his confidence. And for those people, he did some very helpful things. When the Navy contract officers would come around and complain that we were spending too much on travel or weren't adhering to the letter of the rules about how we would handle expenses, Nat Sage would listen to them and he would accept their letter of criticism and he would put it in his drawer. That's all that we never heard about it. It was a very nice atmosphere to work in and very encouraging, and it allowed certain of these freedoms to be then distributed down through the organization. The staff of the project was diverse, but very tightly knit. Each played an important role. I can't possibly mention all of them, and I almost hesitate to mention any because of the fact that I must leave out others. But Robert Everett certainly, as associate director, was an absolutely crucial person in the program. I've often described Bob as the only person I've ever known or worked with where, if we differ, I'll give him better than 50% odds of being right. He usually was. Hugh Boyd was executive officer. Charles Adams and Jack Gilmore were in the computer programming and the development of new methods of computer programming. Norman Taylor, as we've said, was chief engineer. Ken Olson developed the memory test computer, and then later some of the early computers at Lincoln using solid-state electronics. William Papian picked up the mainstream for several years of developing the magnetic core memory. Dick Best was a circuit designer of unusual competence. Out of this group, perhaps 100 people moved on into leadership positions in the computer field. Along with those of us who were young engineers on the technical work, we had also various colorful personalities. Harris von Stock, our financial officer, was a radio amateur. He was a graduate of the radiation laboratory. A man, I suppose, of independent means. It must explain the telephone call I got one day when the MIT accounting office called me up and said, would I please find some way to get him to cash his last 20 paychecks. Patrick Utes, who was in charge of the storage tube work, was one of those people you occasionally meet who at first you decide you shouldn't believe anything he tells you. And for some people, that's what you persist in believing. But then there are those people who, when you get a chance to check, and everything you can check on is verified, then you begin to believe what he says. He came to us from being a research associate in the mathematics department to head up our work on the construction of storage tubes. He had been a professional boxer. He had made vacuum tubes for DeForest in the early days of electronics. He had worked with Thurston, the psychologist, on various kinds of correlation analysis. And he'd been admitted to practice law in the Illinois bar. And then even while he worked for us, he would come back from a weekend and say, Yesterday I was flying over the North Pole with some of my Air Force friends. This was in a time when people didn't routinely fly over the North Pole. Whirlwind had a number of characteristics that I think have persisted, perhaps more than the characteristics of other machines of the time. It had parallel logic, synchronous logic in the sense that it was clock timed. This is in contrast to a machine being developed by the Institute for Advanced Study, which was asynchronous. Each operation, when it terminated, initiated the next operation without any central timing. We didn't feel that we understood the control of that and didn't want to go down that line. The magnetic core storage, the marginal checking, high reliability, cathode ray tube displays, light gun, and a kind of time sharing were all a part of Whirlwind. Out of the project came an impact, I believe, on a number of companies and organizations. Engineering Research Associates, later to become a part of Sperry Rand, built a computer called the 1101. Norman Taylor commented on it when he saw what it was, that it looked as if they had been operating out of his desk. It was really the logic of Whirlwind using a magnetic drum instead of storage tubes for storage. The laboratory, in order to develop with some reasonable facility the variety of electronic equipment that we had to work with, went through the process of developing a full line of logical test equipment, flip-flops, gate tubes, and various logical elements that could then be plugged together in any combination, having enough output drive power to drive anything, and where you could just plug them together according to the logic diagram without having to worry about whether you would load them down or not. A flip-flop in that equipment was 16 inches long, 4 inches high, and 6 inches deep, if you want to compare it with one of today's component within a chip. That test equipment not only served our purpose, but it looked important enough that the Burroughs Corporation made an arrangement to manufacture it and sell it commercially. And they used it as the logical elements out of which Burroughs made its first full-scale digital computer. And then Burroughs lost interest in the line and did not revive it and did not modernize it. And in many ways, the process was played over again in the early days of Digital Equipment Corporation, which, as you know, started by marketing a line of plug-in logic units and then begin to use those to make various more elaborate pieces of equipment, and moved on into the modern company. The impact on IBM was substantial through their relationship to the Sage Air Defense System, because they were the contractors to the Air Force for the computers that went in to the North American Sage Air Defense System. That was a system that had some 35 control centers over continental US and southern Canada. Each control center was about 160 feet square, 4 stories high, and contained 80,000 vacuum tubes. It was the last big vacuum tube system. We were under a great deal of criticism for staying with vacuum tubes. The transistor had been invented by that time and demonstrated, but we felt, and I believe correctly, that it was going to take a long time before it would reach the kind of reliability that we had already achieved with tubes. As has already been mentioned, the MITRE Corporation is an outgrowth of that work, and the System Development Corporation came into existence to provide the programming for the Sage Air Defense System. Through all of this was a running battle on financing and support. The project was looked at as impossibly and unjustifiably expensive. The production, the development of the Whirlwind computer, including the development of all of the components, no counterpart of which existed when we began, including the development of first the cathode ray tube storage, and later the replacement of it with magnetic core storage, that entire process running from 1945 to around 1953 cost a total of about $4.5 million, which today doesn't seem like much. Then it struck most people as grossly expensive, but from it have come a number of developments in the field, and all of you now are carrying on more than I am. I have left the field. I left the field in 1956 to move into some new pioneering in how to analyze social systems and economic behavior. And in the present context, for me personally, this Whirlwind experience was a very good beginning because we learned the problems of pioneering. We learned the need for courage to stand up for what you believe in. And through the years, that certainly has been true in the field of economic analysis. There's a lot of opposition to new approaches there, just as there was opposition to ideas as new as the digital computer. It's a pleasure to be with you, and we'll see what the next 25 years bring.
At what point in your thinking did the concepts for the computer evolve to the idea of a unit that might be mass-produced or produced in units of more than one?
I'm sorry, I missed the last part of that. Evolved to what?
To machines that might be produced in units of more than one. The idea of a general-purpose design as opposed to the kind of single machine used to solve a single set of either engineering or mathematical problems.
From the time that we began to talk about military combat information systems, which was certainly as early as 1948 and well before Whirlwind had operated, we were talking about an application that dealt with machines that would be elsewhere and in multiple copies. And so the idea of trying to develop something that could be replicated came into the picture relatively early, a year or so after the beginning of the design of what became the Whirlwind computer. Now, whether it was before that or not, I don't know. There is the evidence of the reports of the military control combat information center applications in 1948, but I don't remember just what sequence of thought or discussions might have led up to writing those.
Whirlwind ever used for what it was originally budgeted for as a test equipment for airplanes?
No, it was never used for an aircraft analyzer, except as it was used as a digital computer for studying such problems. I think maybe there was even a reference to it in the movie. I've forgotten the details, but only as a scientific calculator and not in the sense of controlling a cockpit and the controls of the airplane.
What kind of studies are you doing now? You were talking about social systems and economic systems. Are these software projects, or tell us what you're doing now with your skills?
Since 1956, we've been engaged in developing a field called system dynamics. It is the way, and this, you see, goes back. It really builds on everything that I had had any experience with. It goes back to the work on feedback control and servo mechanisms under Gordon Brown in the 1940s. It builds on the ideas of simulation and the use of digital computers. And it builds on the management experience in bringing that Whirlwind computer and the Sage Air Defense System to successful completion. I believe that while I've stressed more the technical side, one should equally stress the managerial side of new technology. The two must go hand in hand. In any case, by 1956, I came to the feeling that I didn't want to pursue the electronics side anymore, and it had seemed to me that the managerial side of science, of technology, was in many ways more important than the scientific side. And through a set of very happenstance, casual meetings in the hall and one thing and another, the opportunity opened up for me to go to the management school, to see what the linkage between a management school and an engineering environment might be. That was the charter, to try to carry out a vision that Alfred Sloan had had when he gave the money for the starting of the school. I thought, and other people thought, that it meant either the use of computers for management data processing or the field of operations research. Neither of those looked like the thing to go into after a year of considering why I was at the management school. And gradually there evolved a coalescing of these earlier fields into an effort to understand why there are business cycles, why in some industries like household appliances and automobiles is employment so unstable and fluctuating. Why do some companies gain market share and others lose, even when they're in the same industry with similar products? And so this became a process of simulating the behavior of such systems based on the knowledge that exists within the organizations, rather than based on microeconomic or macroeconomic theory as it has been handed down through the years. How does the actual organizational structure, how do the actual policies being followed by people produce the behavior? And so in the current context, we have extended that work from the corporation to the study of cities and now to the study of national economies, basing the economic work on the understanding we had acquired over nearly 20 years of how corporations operate, and beginning to show that the puzzling behavior of the macroeconomic system, the puzzling behavior of the economic system as a whole, in fact, is generated by the policies and the information flows and the decision-making methods that are known, are common knowledge in the corporate and governmental decision-making areas. That if you take the structures that people talk about, that they know are there, and you put these together into what amounts to a role-playing simulation model, you will find that this substructure, this microstructure down in the economy itself produces business cycles. It produces the economic long wave, which is that process that we think has given us the Great Depressions of the 1830s and the 1890s and the 1930s, and an underlying dynamic that caused these episodes to come along at about 50-year intervals. At the top of one of these long waves, one should expect a decline in new innovation, a faltering of the rise in labor productivity, rising prices, declining capital investment, declining return on investment, excess capacity in many industries around the world. And these are essentially now the headline materials in the business press. There is this underlying dynamic, we believe, highly controversial, but it's to shed light on situations of this sort, on how you can get inflation and unemployment or stagflation at the same time, that we are addressing our effort. And we have computer models now that do all of these things and show a linkage between the underlying structure and information flows and decision-making processes and the total behavior.
I'd like to invite you to join us in the museum for refreshments.